Have you ever wondered where the whole avocado as a display of intergenerational wealth thing started? Well, I found these ink and pastel drawings from the 1770s recently, which show an extravagant French queen lording her hall over the poor. Except I didn't, because these are entirely fake pieces of art, generated by a piece of world-leading artificial intelligence. Using DALL-E 2, you can describe anything you want, and then it'll create a picture of it for you. It's an AI research prototype currently being tested by a small group of advocates and academics. You can ask it to show you what a future Australian Prime Minister might look like. You can ask it to see what a future Australian Prime Minister would look like if he was running late for the bus and was quite stressed about it. You can ask it to show you what Sally McManus would look like if she was made entirely out of cotton balls, speaking to a rally of people also made entirely out of cotton balls. You can ask it to show you what Kevin Rudd would look like if he finally got that fair shake of the sauce bottle. It's a bit of a lark, there are more funny examples ahead, but there are substantive questions here too. Like, how does this even technically work? What does it tell us about the future? And does that even matter? So to begin answering these questions, we've got to go back a few years to 2015, where a major innovation in AI research was automated image captioning. So for a while, machines had been able to correctly label objects and images. So for example, it could tell us that this was a cat. But all of a sudden, researchers were able to take those labels and arrange them in natural language descriptions. So much the way we may describe them or we may tell people about them. This made searching through large bodies of images much easier, and it also made the web much more accessible to people with visual impairment. And this discovery made one group of researchers wonder, what if we swap those around? If you could take an image and generate some natural language text, could you take some natural language text and generate an entirely new image? And not just a new image that cuts together a bunch of things that already exist, but can it create an entirely new image that the computer has never seen before? Can it use a type of imagination? So for example, could it show us what purple bananas might look like? And they pulled it off in gloriously low resolution 32 by 32 pixels. So let's zoom in on that. I suppose it's the thing, but the 2016 paper still proved that it was possible, even if there was heaps more work to do. And then, barely months later, that became this. DALL-E is built by a US research lab called OpenAI that seeks to establish a good precedent by developing effective and efficient AI systems that are also deeply ethical. If you're an avid meme lord or young person on the internet, you've probably seen a bunch of things that look like DALL-E's outputs float through your feed over the last few months. Many of these have been created by other tools, such as Crayon or Midjourney, that mirror many of DALL-E's techniques and methodologies, but with much less sophistication and at a much smaller scale. The challenge with them is that they're just much narrower in focus. This is actually a perennial problem with AI, is that it can get very good at doing a very small specific set of things, such as generating images that look very realistically like humans, or spotting brain cancers, or getting very good at listening to your instructions to play a certain radio station. But there's not a lot of breadth. DALL-E isn't like that. It's remarkable because it can be used in a multitude of different ways to create a multitude of different outputs. For an image generator to be able to respond to such different cues, it requires an enormous amount of incredibly diverse training data. For DALL-E 2, that includes hundreds of millions of images sourced online, as well as the text metadata that accompanies it. That's the text that's kind of hidden out the back to make the web more accessible and to help conventional search engines that can't read images. How very antiquated of them. But once we've collected all of this stuff, what does the AI do with it? We might assume that given a text prompt, like a golden retriever driving a convertible on the beach, that it skims through the training data, finds some corresponding photos, and just copies some of those pixels over. Just chucks it in there. But that's not what it does. The newly generated image doesn't copy elements from the training data, it is wholly original and a new image, emerging from the latent space of the deep learning model. I'll come back and explain latent space in a second, but the new image has to be wholly original because of the way the model learns. Have a look at these three images. Which caption goes with which image? If you finished kindergarten, it should be a breeze. But this is what the computer sees. Just a grid of pixel values for red, green, and blue. You need to just guess, and that's what the computer does at the start too. Maybe that bit's the car. You could do this thousands and thousands of times and never improve. And the computer starts that way too, but it doesn't get bored and it doesn't forget when it gets it wrong. It just keeps going and going until it gets it right, eventually figuring out which combination of pixels is associated with the word you've used. And that's essentially what deep learning is. It's a computer fixating on a problem for long enough to start identifying patterns. It identifies and scores these patterns, looking for qualities that can separate images or concepts mathematically. For example, if we wanted to tell the difference between an apple and a tennis ball, then perhaps we could start by measuring the amount of red in an image, putting the apple over here and the tennis ball over here on a one-dimensional axis. Simple. But color alone doesn't define whether one object is an apple or a tennis ball. We can have green apples too, so we need to add some more variables. Maybe we can add another axis and score their shape, for example. Apples have a distinct outline, and so do balls, but then we run into another problem. Some apples look a little bit like tennis balls. So maybe we add a third dimension, such as tennis balls typically have white stripes and fuzzy skins, when apples typically don't. And now we've created a three-dimensional space. And ideally, when we get a new image, we can measure those three variables and see whether it falls in the apple region or the tennis ball region of that space. But what if we want our model to recognize more than just apples and tennis balls, but all sorts of other objects? Redness, shape, and lines don't fully capture what's distinctive about these objects. So that's what machine learning algorithms try to do, try to spot what's distinctive as they go through all of the training data. Using all of these different variables to improve their judgment and building out a mathematical space in way more than 3 dimensions. DALL-E 2 ultimately creates more than 500 axes representing variables that humans wouldn't even recognize or have names for, and is quite hard to visualize here, but the result is that the space has some meaningful clusters. A region that captures the essence of appleiness, a region that represents the textures and colors of photos taken at the beach, an area for snow and an area for golden retrievers and convertibles and somewhere in between. Any point in that space can be thought of as the recipe for a possible image. The text prompt is what navigates us to that specific location within the machine's latent space. A latent space, told you I'd come back to it. It's the universe of all of these different variables. It's one of the 2 technologies that make DALL-E so special, which its engineers call CLIP. But there's one more step that's just as impressive. Once we've found the right spot within this mathematical space, we then need to create the image, using the second remarkable technology in DALL-E called diffusion. Diffusion hopes to take what the computer is seeing and turn it into something that makes sense. Technically, it starts with just noise, and then, over a series of iterations, strips it back and arranges the pixels into a composition that looks attractive to humans. It's the artist. And due to some randomness in the process, even if you enter the same prompt, you won't necessarily get the same image. And if you enter the exact same prompt into a different model made by different people with different training data, you'll get a radically different result because you're in a different latent space. There's also still a huge bunch of technical challenges as well. So for example, it's quite bad at objects in relation to each other. If you ask for a red ball on top of a blue box, it'll screw it up. It's also incredibly bad at words. For example, this is meant to be the solution to climate change. But the risk of misuse is really its greatest challenge. This thing can spin up misinformation like crazy. And that's kind of part of the reason that OpenAI built it in the first place, was to identify some of these challenges, see how they manifest, and then preemptively create solutions to them. It doesn't include violence, nudity, or specific people in its dataset. And because these ideas and concepts don't exist in its latent space, it can't create them. It literally doesn't know that they exist. Although, as we saw from our examples of Sally and Kevin Rudd from before, it does have some sense about who these public figures are, even if it's technically not meant to. More concerningly though, is often unseen forms of social bias. So for example, I'm sure you noticed that every single version of the future Australian Prime Minister we looked at before was an older white man. Also, if you were to look up images of nurses, you'll disproportionately get women and women of colour. And in one open source dataset, The word Asian is represented first and foremost by an avalanche of pornography. It is an infinitely complex mirror that reflects back to us the patterns and signals we thought were appropriate to place on the internet in the first place. So to wrap up, it's clearly incredibly technically impressive, and I think it's important to understand how it works because the rate of change is so staggering. And it's only going to become more exponential as new capacities like quantum computing come online that will allow us to both collect larger data sets, create even more complex latent spaces, and radically speed up our ability to do that sort of processing itself. I think it also presents a whole bunch of compelling social questions, such as what does this even mean for art? What does it mean to be an artist? Does this open up a whole bunch of extra capacity for people without technical creative skills to begin expressing themselves? Also, what does this mean for society more broadly? Lots and lots of questions. Also, if you have any ideas, feel free to suggest them below and I'll post the photos.